Hey guys, how we doing?
Welcome to 6.3 and beyond.
You sound awfully excited, Mr. Bedell.
It's almost Christmas. See the guys
Yes.
skiing around here. You know, we're like.
Not for you guys, but when we're recording this, it is. So.
Yes, yes. So hey, this is 6.3, and this is similar polygons. And first thing I want to point out to you is the symbol right next to the word similar polygons, and that symbol is called a
Tilde.
tilde. See, I didn't know that. See, thank
There
God
you
Mr.
go.
Scritchfield's here because
Yep.
I would have just ruined that one.
Computer term.
I just call it the little squiggly half the time.
Squiggly. That's what we'll call it.
But the tilde, notice that it is the top piece of congruent without the equal sign underneath. And so that is the symbol for similar. So we won't use an equal sign when we're talking about similar, but we will use a tilde, which means the same shape but can be a different size. And if you look at the two triangles right below there, you see that they're pretty close to the same shape but different sizes. And basically the idea is for things to be similar, they have the corresponding angles are congruent and the sides are proportional. So we've already kind of talked about proportionals and the ratios and how those things can kind of look different but break down to be the same thing. It's kind of the idea when we look at these triangles. They're of different sizes, but if you kind of shrink down one or make one bigger, it eventually becomes the same thing. And so you have this idea of corresponding angles and proportional sides. Anything you want to say?
Well, I'm just noticing that the diagram, we tried to fix this diagram, guys, right before we started, but it's hard to see the diagram there on the bigger triangle. The side between the 110 and the 40, there's an 8 there. And so you can't see it because it's blue and it's on a blue background. Right when the skier goes by there, you can see it. And so there is a proportion going on here, or there's a ratio set up between the sides. It's just hard to see that. But the 20 and the 10 you can see, so that's 1/2, and then that goes from 8 to 4. Those sides are 1/2, and there's probably a 13 over there too. Let's wait for the skier to get there. I didn't see it, but there's probably a 13 over there to where the bottoms are 26 to 13.
So I think that one comes in.
Oh, does it?
I think so.
Okay.
But hey, real quick, guys, look at the angles here. So you got a 40-degree angle at D and then a 40-degree angle at F, and then it's 110 at B, and they don't give us, we don't have E here, but it's 110 at B, and then it's over at F, it's 30 degrees on the smaller triangle. So if you go 40 plus 30, that gives you 70, and so E is 110. So you can kind of see how all three angles are similar, because if you do 40 and 110, that gives you 150, and then 30 left over. But here comes that 13 right there.
There it is.
So as you can see, as Mr. Scritchfield was already pointing out, D to E and A to B were of a ratio of 1/2, because 4 to 8 is 1/2 if you reduce that down. E to F and B to C were 10 to 20, which also reduces down to 1/2. And then D to F and AC is a ratio of 13 to 26, which is also the ratio of 1/2. And there's that whole thing with angle A is congruent to angle D, angle B is congruent to angle E, angle C is congruent to angle F. Now, pay close attention to that, because we're going to talk about that again later on in the PowerPoint. And then there's your corresponding sides that are proportional to one another. Anything else, Mr. Scritchfield?
Nope. Just that the sides are proportional and angles are congruent. That's the important part about similar polygons. So there's that scale factor going on. As in the last triangles that Mr. Bedell was just talking about, that either the scale factor of 1 to 2 or 2 to 1, the ratio of two corresponding sides of a polygon is that scale factor. From the first section, we referred to it as a ratio. And if we set up more than one pair of the sides from the two shapes that we're talking about, it would set up a proportion. And so the question here is, are these two shapes, and notice on the last slide we said similar polygons, not necessarily just triangles, although we're going to focus on triangles, but it could be any kind of shape. And so any polygonal shape anyway. So they're asking us here if these two quadrilaterals on the bottom here are similar. And so the way we would figure that out is by looking at the proportional sides, corresponding sides, to see if they are proportional. So if we compare the top to the top, 39 to 26, so RS to AB there, okay, and then we go 12 to 8
SU.
as the right side of each shape. Is that what that is? SU to DB, right? 21 to 14 is the bottom, and 18 to 12. Now the question is, do all of those reduce down to the same thing? And if they are all proportional in the same ratio, then they would be similar. And so we see that they all reduce down to 3 to 2. The 39 to 26 is 13 goes into both of those. 12 to 8, 4 goes into both of those. 21 to 14, 7 goes into both of those. 18 to 12, 6 goes into both of those. So they all reduce down to 3 to 2. Okay, so since the sides are proportional, those two quadrilaterals are similar to each other. Okay, anything else there?
Nope. Well, I guess one thing, Kevin, is they don't talk, Mr. Scritchell, they don't talk anything about angles here.
They don't. Yeah, and because of the shapes that are going on here, we can see that the only way to build a quadrilateral with those side lengths would be if the angles fell into place. And we'll talk more about that as we progress in today's lesson, where we essentially have shortcuts to finding these things. Kind of like we did with the triangles when we were proving them congruent. We ended up with some shortcuts there. We're going to have some shortcuts for similar as well. So.